Let's make sure everyone can see it. Can everyone see the screen?
Yep, looks good.
All right. Awesome. Okay. Hello, welcome. Thanks, Robert, for having me here to present. It's great to be here. So my name is Nika Korchok, and I'm going to be presenting my talk entitled, "I'm Sorry I Rooted Your Smart House. I Wish It Was Mine," a modular anthology guide to go from zero to hardware hacking hero, or at least learn how to pop open a shell on your smart fridge. So, all right, zero, who am I? As Robert mentioned, I'm an independent security researcher and reverse engineer. I've been working on an independent security research project for about the last year related to IoT and embedded device security, and this talk stems from that work. I'm also an artist, and you can find me on Instagram and Twitter, and my website is right there. So my experience with hardware hacking has been mostly in the past year. I got into it in April 2020, and before that, if I'd looked at a PCB or a printed circuit board, I wouldn't have been able to identify anything. And now I can find pinouts, I can identify chips. So I'm proof that you can go from zero to, some positive integer. I don't know if I'm a hero right now, but I'm definitely, my skills are much improved. So I'm here to share some of that knowledge with you and hopefully inspire you to start some cool hardware hacking projects. So this is our agenda. So just a kind of a brief overview of how the talk is structured for today. It's roughly divided into three parts. The first part is more theory-based, so it'll give you more definitions, background information on hardware hacking. Part 3 is practical, so it's going over a demo. And then part 2 is talking about setting up your hardware hacking lab. Now, throughout this, I'm going to be sort of going back and forth between some of the theory and the practice, just to illustrate each of these examples that I'm defining in the theory section in part 1. And if anyone has any questions as we're going through the part 1 or part 2 or anything, feel free to just jump in and let me know. But yeah, that's the overview of how the talk is structured. This is a bit more detail of some of the topics I'm covering in part 1, just so you're aware. And part 2 is creating your hardware hacking lab. And part 3 is breaking some stuff. So, okay. If there's no questions, I'll keep going. Okay, so why should you want to learn about hardware hacking and embedded device security? Well, it's helpful to know the basics because as Anna Wintour famously did not say, but she's saying here in this meme I made, patching your firmware is always in style. And in other words, having the security of your organization breached because no one patched the firmware on your smart fridge in the company break room, it's not a cute look. So it's helpful to know what firmware is, how to patch it, and then also how IoT security can be extended, or hardware hacking methodologies and reverse engineering methodologies can be extended to different cool projects, not necessarily related to security, but more creative pursuits. In that vein, my motivations for learning more about hardware hacking and embedded device security were actually to apply all of my hardware hacking skills to creating Mr. Robot-esque art installations using an IoT art botnet, but basically just being able to apply reverse engineering and hardware hacking skills to cool new art projects. So there's lots of different use cases, and hopefully this will inspire a couple of you or all of you to get started with them. So for this talk, I'm going to be talking about the reverse engineering methodology that I've been using in my hardware hacking and IoT security pursuits. I'm sure other people have different methodologies, but this is the one that I've come up with that I find the most helpful. So step one is recon and research. It's reading data sheets for the device, identifying important components, and then also compiling related research on the device. So looking at different CVEs, research papers, trying to find anyone else, the work of anyone else who's already researched and found an interesting vulnerability. Part two is identifying points on the device, as well as important chips or just any important component that you could use later. So part three is serial console setup and analysis. 4 is obtaining a firmware image. 5 is analysis of the firmware image. 6, vulnerabilities, vulnerability identification or identification of interesting vectors of further development or analysis. 7 is exploit development, but it could also be development of cool art projects, what have you. But anyway, reverse engineering methodology, but make it Euclidean because we all like nice graphs and pictures. So here's just our reference flowchart that I'll be referring to throughout the presentation. So any questions so far?
Just a general one. When you said you're getting data sheets and other kinds of things on products and so forth, how difficult or easy sometimes to get that information? Is it readily available for most products? Let's say, for example, your smart fridge and how it works and so forth. Is it easy enough to get that technical info, or do you have to dig a little bit? Or I'm just generally curious, I guess, on that.
Yeah, that's a good question. I would say it very much depends on whatever device or whatever device that you're looking at. So for this talk, I have one device specifically that I looked at, and I did have a lot of difficulty finding data sheets, both for the board and also for each of the chips that I identified. So I'll go through that and just talk about some helpful hints that I've come up with in terms of being able to find those data sheets. But yeah, it can definitely be challenging. It depends on the company in terms of what they share and what they want to disclose to people.
Sure. Okay. Thank you.
Yeah. Okay. Right. So. Okay, so just a quick note on the format of this presentation for some of the slides so that it's clear. So I already mentioned the overall structure, part 1, part 3, part 2, theory and practice. But for these slides, I just wanted to make a note. So some of the slides, especially in part 1, will have this structure where it's the right side panel will be an image, and the left side will be a descriptor of what the image is. These are scanned copies of my notes that I've taken as I've been doing research over the last year, and so I just wanted to make them available to anyone else who wanted to use them. So they're sort of just I guess quick cheat sheets on different topics to give you a more detailed technical overview to use as reference materials. So this one is circuit schematic symbols that you might encounter when you're looking at a data sheet for a particular device. And here's another one on logic gates. So I won't be going into a ton of detail on each of these specific notes, but you can refer to them later. I will make the slides publicly available. I wanted this presentation to serve as an educational resource, so you can go back and refer to it and just dig deeper onto any topic that you find really interesting or maybe confusing and want to just spend more time on. So, okay. So with all that said, let's get into some of our definitions. So part 1, embedded devices. What is an embedded device? Well, an embedded device is essentially a little computer, little tiny computer, can fit in your purse, or maybe it can't if you have a smart fridge. But it's a small computer that's essentially, it's a small computer, and it will have two different distinguishing features that make it different and potentially slightly more challenging, or just different to adapt to than hacking on a regular desktop computer. So the embedded device that I used for this presentation is a FOSCAM F19821W. Firmware version is this. It's from 2013, and I got it at a yard sale, so which is a good tip for anyone who wants to get into this and doesn't want to spend a ton of money buying new embedded devices. Goodwill and yard sales and things like that are good places to find old equipment that other people don't want anymore. Of course, practice precautions when using old or devices whose origins you're not entirely sure of. But it's definitely a good place to start playing with and start experimenting with in a hardware hacking lab. So, and I'm just going to, there we go, okay. So just briefly to talk about two of the features or challenges of hacking embedded devices. One is it's headless, which means that there's not an associated monitor to go along with the device. So like I said, it's a small computer. You just have the board. Sometimes it can be multiple boards, but there's no monitor. So if you want to have a terminal emulator up and see what's happening as the device boots up, you need to set up a serial console to be able to access all of that and observe and monitor important processes as they're happening. Another unique feature is that it's going to run an architecture that will almost certainly not be x86. So if that's the only architecture that you're familiar with, you will probably have to learn a new assembly language. For this project, I learned ARM, and I've been working on that primarily with devices. But there's also, many other architectures. There's MIPS, there's PowerPC, there's lots of others. So it'll just depend on the device that you pick to work with, and but it's fun. ARM's really cool. I love it a lot. So it's a fun challenge. But and then I'm just going to go back to this here. Just a couple helpful points to point out as you're starting out and getting up to speed with whatever device that you choose. The first thing that I like to do as part of that part one in our reverse engineering methodology, a part of the recon and research phase is just looking at the device that you have. So you're going to be looking at all of the angles. If we can go back to this one, you can identify all of the different connection points. There's an Ethernet port there. And then if you turn the device over, so this is on the bottom of the device, sometimes you'll have handy stickers. And here our handy sticker has our default admin credentials, which are admin and blank. Several of the other research papers and presentations related to this device that I watched mentioned this and talked about finding this later in the process, but it's actually a pretty quick thing to find just based on the sticker that you can see on the bottom. So it's a helpful hint, I guess. All right, opening up the device, it's going to just require different screws and potentially different tools depending on the make and model of the device that you're looking at. So one thing that I found really helpful when I was working on this is to Google or YouTube search teardowns of anyone else who's already taken apart a device that you're working on. So if you YouTube search FOSCAM with this model number, you can watch other people taking apart the device, which is really helpful because if you're looking at an embedded device and there's stickers over the screw heads, you might not know that that's there initially. So just part of the recon phase to be able to continue exploring the device further. So, And then here's our final PCB after we've disconnected everything from all of the wires and just put it on a flat surface. Okay. So, all right, so we've taken apart our device, we've looked at it, we've made some notes about important stickers, important default credentials. The next thing is firmware. And what is firmware? So firmware is the intermediary piece of software that serves as the interface between software and hardware on a device. It can be similar to an OS kernel. It can be the actual it can hold the operating system of the device itself, or it can just be the BIOS, which is the basic input-output system on a desktop computer. So it'll really depend. When you say you're looking at firmware, the firmware image can be a lot of things, and it can contain a lot of different files, or it can only be, one compressed kernel image. It really depends. But where does firmware live? Firmware tends to reside in read-only memory or ROM. So it'll be on something that's either an EEPROM chip, a flash chip, something on the device. For this example here, the firmware is on a serial flash chip, and that's usually identified as being a small chip with 8 legs, as I'll point out later. But firmware lives on ROM. So, and in the case of embedded devices, the firmware image can contain a variety of interesting files for your hacking purposes. So, like I mentioned, binaries that either the kernel, also binaries that help for running different services on the device. It can contain readmes, it can contain instructions for how to update the firmware, contain image files. It's really it just depends. So in our case, how do we get the firmware? Right? Okay, so we want to play around with the device. We want to modify it. We want to do something cool with it. Firmware is usually a really good way to go about that, because the firmware on an embedded device is going to control the majority of the functionality. So how do we get the firmware? There's 3 main ways that you can approach it. The first one is directly from the vendor's website. The second is doing something like sniffing the traffic during a critical process, like the boot process or a firmware update. And then the third would be to interface directly with one of the chips to obtain a copy, like interfacing with the serial flash chip using SPI or I2C or whatever protocol it uses. But let's start with the simplest, easiest example. Let's try going to the vendor's website. And if we go to the FOSCAM website, we can download an image directly there. Again, as I mentioned, this is a very old camera. It's from 2013. The firmware version is also from 2013. So I'm going to just go ahead and download the one that's from 2013. Okay, so we get our file. We run a couple of preliminary diagnostic tests on it, right? So we can run the file command, like the built-in Linux utility. So we run file, and the output from file tells us that the firmware image is encrypted with OpenSSL. Okay, interesting. So what can we do with that? Well, we don't know if it's actually encrypted with OpenSSL. This is giving us a good indication that it might be, but we probably want to verify it with another Magic Byte utility. So let's run it with binwalk. As I just said, binwalk is a utility. It's a Python script. It's open source. It's on GitHub, and it's really helpful for identifying magic bytes and file signatures in an input file. So we run binwalk on this file, and it tells us that yes, it is OpenSSL encrypted, and it's salted, and the salt is this. Okay, great. But we still don't know what the cipher is that we're using for the OpenSSL, and we don't know what the key is. Well, we could brute force it, and we could hope for the best and run a bunch of word lists, or we could just look at some of the research that other people have done, see if anyone else has figured it out. Oh, and someone did. So This is why it's really helpful to do that preliminary research recon phase. You can find other work that other people and other researchers have already shared. This one comes from, I believe, the team at BDOO or BDO, I'm not sure how you say it. And it was their proof of concept for their analysis of the FOSCAM, I think different models of the FOSCAM cameras. So there's a proof of concept piece of code on GitHub to decrypt the firmware image. And it also contains helpful information like commonly used keys and also the cipher that's used. So perfect. You can either adapt it or use it as is, but when I was doing my analysis, I just tried it with the first key on the list, thinking maybe because it's a very old firmware image, it would be one of the first ones. And then I ran it with the cipher, which is listed as, don't know if you can see it in here, but the cipher that's used is AES 128 CBC. So if we run it with that command, as we can sort of see on this screen where it's the command equals, we run it with that command and then just substitute in cipher with AES 128 CBC and then key with the first key on this list. We get our decrypted firmware image. Cool. All right, so we have our decrypted firmware. Let's start looking around, seeing what's there. Okay, so if we look at some of these, I'm just going to highlight a couple of the interesting ones, and then I'll keep going. So we have our shell script that's our boot. We have our firmware upgrade config, a bunch of other text files, and then if we unpat or untar this this app.tar, you can go into the app directory, which is here. So, and then that contains a lot of interesting other files that we would potentially want to look at. Again, as you're exploring a firmware image, like I said, there can be a lot of different formats of it. You can, you might decrypt it or decompress it and not get as much information out of it. But in this case, there was a good amount of information. So as we're exploring this further, we can look at some of the files that are in the bin directory. One of the files that's in the bin directory, just to highlight it here, is the firmware upgrade utility. And then when we're checking our firmware upgrade utility, I just ran strings for some initial analysis again. It reveals that the decryption command is hard-coded along with the key. So there it is again on like the second line, 184, OpenSSL encrypt. There's the cipher and there's the key hard-coded in to the firmware image. So cool. Another interesting thing that I found when I was doing this initial firmware analysis is that in the firmware config XML file, it mentions that there's different partitions or different, I would assume, partitions, parts of this of the firmware, but we only have the one that was the app directory, if you remember from here. So we only have an app directory. We don't have any of the other ones mentioned. We don't have a ROM. We don't have a U-boot. So that indicates to us that we might not have the entirety of the firmware. So we might want to do some more research, more extraction to get more information out of the device and out of the chip. Okay. So these are just some highlights of other interesting files that were extracted as part of this decryption and extraction from all of the firmware analysis from the vendor website. Okay. Oh. So going back to our reverse engineering methodology, like I said, we're going a bit back and forth between theory and practice, but I wanted to highlight what an actual firmware image can look like, and a firmware image from a vendor website versus a firmware image from the device itself. So again, we went through some of the initial recon and research. We identified areas. We're going to be identifying areas of interest. So let's go on to that. So integrated circuits on the board. If we look at the board, there's two sides that are actually interesting. So we have chips on both sides. We're going to be identifying integrated circuits, or ICs, that look interesting to us. So on the right side, we have our highlighted areas of interest. So we have a potential processor, potential there that we want to check. And as we're doing this, as we're looking at the device, as we're inspecting all of the interesting chips, we want to be writing down, and most likely using a magnifying glass because they're written in very, very small writing. We want to write down the serial numbers or identifying information on any of those ICs so that we can look up the data sheets later. So, and again, on the other side of the board, we have these two. And I'm just going to give you a spoiler here that the H1358 is the processor that we want. Again, we repeat the same thing with the flash chip. So we identify potential ICs on the board that could be the place where the firmware is stored. Again, as I mentioned, in this case, the flash chip or the ROM where the firmware is stored is on a serial flash. It can be on a different format of a chip. It can be on a NAND chip, which will look different than this, but just for our purposes here, the flash chips all look like little spiders. They have 8 legs, and they all have their identifying part numbers on the top, which we can use to cross-reference and Google and see if we can find out what ICs are what and which ones are the ones that we're interested in. So, and again, both sides of the board, because just like 2, 5, 10 chips wasn't enough. So we have 3 more candidates on this side, and then again, to spoil it, it's the one on the lower right-hand side, which is not this one, this one. So our flash chip is the MX25L12835F. Cool. And this is some of the excerpts from the data sheets that are available on the Macronix website. As I said before, some of these were difficult to find. Some of them didn't have any clear, some of the writing on them wasn't clear. So that's another potential hurdle if you're trying to identify them and you're working with a device where maybe it's older or maybe any of the identifying information could be scratched off. It's not always very easy to confirm the serial number on any of the device, on any of the chips. But thankfully this one I did confirm it. So there we go. Okay. Are there any questions right now before I keep going?
No, you're doing fine. It's very interesting.
Okay.
Yep, no questions in chat. Thank you.
Cool. All right, cool. All right, so moving on from that. So we've identified our interesting chips on the board. What can we do with that, right? So here is, again, another piece of my notes. So this is just a simplified view of communication between 2 computers. The important thing that you have to know here is that when 2 computers are communicating, it's going to be taking a parallel input, converting it to a serial output. The second computer is going to be taking it as a serial input and converting it into a parallel output. Might not always be the case, but this is a general simplified overview of communication. So in considering that, we want to be thinking of our 2 main, in considering that, we want to be thinking of what protocols are going to be used for different chips to talk to one another on the board, right? So if we want to get information like the firmware image out of any of the chips, we want to know what language they speak or what protocols they speak. So this is another area where looking at the data sheets can be helpful for knowing whether a chip speaks SPI or I2C, if there's a serial port on the device, which will speak UART, and I'll cover that now. So these are 2 potential UART headers. I'm just going to be jumping ahead here real quick. So UART, again, when we're talking about talking to a device, UART is one of the primary things that we're going to be using. So UART stands for Universal Asynchronous Receiver and Transmitter. It uses 3 pins, technically 4, but we're not going to be using the 4th, which is VCC. But it uses 3 pins, receiver, transmit, and ground. The important thing to note when you're connecting to a UART, or when you're using UART to communicate with a series of pins, you want to connect the RX pin of one device with the TX pin of the second device. The TX pin of first device with the RX pin of the second device. It's just ensuring that the message is going from the right end to the right end. Otherwise, you're not going to be getting any information. So the other important thing to note about UART is that it's asynchronous, which means that it's not using a clock to sync up the information that's transmitted between the 2 devices or 2 computers. So it's going to be using a couple different things to ensure the successful transmission of data. So those things are an agreed upon baud rate, which is going to be your bits per second of transmission, your frame size, and your parity, and your start and stop bits. So 4 things. The frame at the top on the right-hand side just gives an example of frame. And these are going to be also more information that you're going to find out in looking at data sheets and in related research on that device or on similar devices. Sometimes it's just a guess and check in terms of things like baud rates. And then sometimes a data sheet or a user manual of a device can reveal a lot of that information or all of it. So it'll really depend. But UART is the protocol that's used when you're setting up a serial console on a device in general. Another important thing to point out here, just as an aside, setting up a serial port can sometimes use RS-232 instead of TTL. This is just getting a bit more technical, but again, it's just going to be something you verify by looking at data sheets or further research on the device. For the most part, the majority of embedded devices that I've worked with and the majority of embedded devices I've done research on, I'll use TTL. But again, if you have maybe an older device or just a different kind of device, it might use RS-232. So it's just something that's important to keep in mind, especially when you're setting things up so that nothing starts to smoke on the board. So yeah, so I mentioned serial console. So what is a serial console? Okay, so as I mentioned earlier, one of the challenges when working with embedded devices is that it's headless, right? So there's no monitor. You can't easily keep track of what's happening on the device by looking at a screen and seeing the output. So you want to set up a serial console, and a serial console just simply is using a serial port connection to access a computer and allow a user to interact with the device and issue commands through a terminal emulator. So I like using Minicom for my serial console setup. There's also things like PuTTY or Screen. It's just going to depend on what your preferences are, but this is generally what the serial port setup is when I'm working on something. So you enter serial port setup on Minicom, and then enter in all of the requisite information, your serial device, and then those 3 things, like I mentioned, those 4 things, like I mentioned before, for a UART, which are baud rate. Here it's 115,200, your parity, your frame size, and your start and stop bits. So 8N1. 8N1 is pretty standard. I haven't worked with anything that's not 8N1. I'm sure there are things that are. Again, just check your data sheets and your supplementary research to confirm that. So, okay. Any questions, or go into SPI? Okay, I will go on to SPI then. Okay, so SPI is one of the serial communication protocols used for interfacing with chips, especially things that are contain firmware images. So any flash chips or you know, other chips on the board might speak SPI. But SPI is a a clocked protocol. So again, unlike UART, which is asynchronous, doesn't use a clock, SPI does use a clock. So there's 4 pins that are pretty integral to setting up an SPI connection with a chip that speaks SPI, which are the chip select, the clock, and then the MISO or DO, and the MOSI or DI, which are master in, slave out, or data output, and then master out, slave in, data input, respectively. So, and similar to UART, where you're hooking up the TX to the RX to the TX, here you're hooking up, oh no, sorry, reverse of the UART, sorry, that's confusing. Reverse of the UART, you are hooking up the MOSI to the MOSI, the MISO to the MISO. Okay, great. Okay, so those are all of our general definitions, our sort of background information on what we need to get started. So, does anyone have any questions?
I have a question.
Yeah.
Would CAN bus be considered one of the similar protocols to what you've presented so far?
I would say it is a similar protocol in the fact that it's a serial communication protocol. It's not in sort of, it sort of is. I think like in terms of I think like the distinguishing feature of the CAN bus is that it's like using non-destructive bitwise arbitration, and there's not it's different than SPI, where you have sort of this hierarchy of which device gets higher priority. It's structured differently in CAN. But yeah, it's also a serial communication protocol. That was your question.
Yes, thank you.
Okay, cool. Anything else, or we get to move on? Okay. All right. So part two. Part two is a starving artist guide to setting up your hardware hacking lab. So one thing that I encountered, because I am a starving artist, or I just don't like spending a ton of money on, hardware hacking materials when I'm starting out, is that a lot of these things can be really expensive, and it can be difficult to know what to buy and what's really necessary to get started. So I've highlighted the materials that I have in my lab that are A, not too expensive, and B, really necessary to getting started. So there's a lot of other materials that you can buy and that are really cool and do a lot of really cool things, but they're definitely a higher price point. So the ones I've highlighted are significantly more affordable. So the essentials, some of the essentials that you need, jumper wires. They come in different varieties like MM, MF, FF. These stand for male and female, which are odd distinguishing features for a wire, but whatever. But so I've abbreviated it here to MM and MF and FF. But jumper wires are helpful for connecting to different parts on a board. If you have header pins that are male header pins, which I will show here, which look like this, you can use a female to male or female-female connector of a jumper wire to connect to them, which is helpful for interfacing with things like a serial console, like I said before. So yeah, first two things: jumper wires, header pins. You can get both of these on places like Adafruit, Spark Fun, Amazon, pretty cheap. Most of these are available in big assorted collections, and they're in like the range of 3 to 10, depending on how big of a collection of things that you get. So pretty affordable. And then the next thing is a serial to USB converter. This here is actually my bus pirate, which I'll get to in a second, but there's a lot of serial to USB converters that you can get. And again, I'm just going to highlight that it's a serial to TTL adapter rather than an RS-232. So again, this is something where if you have a device that uses RS-232 instead of TTL, you want to be getting an adapter that's fit for that conversion. But a serial to USB converter, I also have another one. If I can, hold on, I have it right beside my computer. It's this. This was like $5 on Amazon, and it's pretty good. But I ended up getting a bus pirate later, so I just like using it for serial to USB connections, setting things up like serial consoles and connecting to UART interfaces. But you can get a pretty cheap and pretty handy serial to USB converter for pretty cheap, $5-10. And then the last essential that you need definitely is a multimeter. This was $30, but it's got a lot of really good functionality. Multimeters are really important for doing things like testing continuity between points and verifying pins on a board. So I'm gonna just rapidly switch back to here. When you find a candidate for UART, so UART is typically defined by 4 pins in a row or 3 pins in a row, not always, but usually. You want to be verifying that each pin is a certain, is one of the 4 candidate pins. And a multimeter is really helpful for doing that. So you can use continuity to check that it's ground, and then also applying things like direct voltage to check which of the 4 pins is the RX pin, which is the TX pin, and then which one is the VCC pin. So those are jumper wires, header pins, serial USB converter, multimeter. Those are the essentials. Any questions? Okay, all right, I'll keep going. So soldering materials. So you might want to solder, or you might need to solder at some point during the process of hardware hacking. Sometimes there are test points on a board that are just test pads, so they're flat, and you can't use a header pin to poke through. Or you can use you might need soldering for a variety of purposes with hardware hacking. So these are the materials that you need to get started with soldering. First thing is a soldering iron, and you want a temperature controlled one so you can adjust it for different settings and also for working with different types of solder. And you also need but you probably would like a soldering iron stand just so that you can rest it while you're working on different components. Flux. This is a silly philosophy joke there for Heraclitus, so you can brush past that, or you're a philosophy fan, there you go. But flux is helpful for making solder flow on a board. It's also really, really critical when you're working with lead-free solder, which is really critical when you're working with lead-free solder, which doesn't flow quite as easily as leaded solder. And then again, as you're working with soldering tools, solder comes in 2 varieties: leaded solder or lead-free solder. Take your pick. I've mostly been working with lead-free solder. It's a little trickier to work with, and it has a higher melting point, so you have to adjust your soldering iron appropriately, but it's not too bad. And then a soldering wick is essentially a copper vacuum that sweeps up excess solder. And then these are other miscellaneous items for your soldering workbench. This is my makeshift soldering workstation. Like I said, starving artist guide. So it's not the greatest, but it works. So, whatever. Other items that you need when you're soldering are either a kitchen sponge or a brass sponge, just for wiping off excess solder off the soldering iron, a razor or straight edge for scraping up extra flux that accumulates on the board, isopropyl alcohol for also cleaning the board, a workbench, and I really like using silicone baking sheets because they're anti-static and they're just good for holding different materials. And then also you might want a vice grip or a helping hands for working with boards and holding things in place for soldering. And then the last thing is safety items, because safety is really important when you're soldering. So first and foremost, safety glasses so that solders, if it splatters, it doesn't go in your eyes. And so just, for any part that's small that could hurt you. Safety glasses are important. A mask, potentially, if you want to just avoid having the fumes breathing in super directly. Having a small fan is also helpful for blowing away any soldering fumes. And then having something like an open window nearby or a suitable outdoor or semi-outdoor space to work in. Really, this is all just related to making sure that there's good airflow so that you're not in a contained space breathing in a lot of fumes of flux and solder. So, all right, extra credit, 2 items. The Bus Pirate, which I really like. It's got interfaces for not all your favorite serial communication protocols, but some of them. So JTAGs by UART I2C. Really handy. And the one that I got came with this nice little braid of jumper wires to connect to different points on the board. And then also a Raspberry Pi. Raspberry Pis are really helpful for, bunch of different reasons when you're working with hardware hacking and embedded devices. One thing is it's running on ARM, so you can play around with ARM binaries in an ARM environment, which is a little easier than an emulator. And then it's also really helpful for running tools like Flash ROM, which are, in my experience, pretty notoriously finicky on desktop computers, but run very nicely on Raspberry Pis. So, and then, of course, there's lots of other extra items, but these are the 2 that I picked, and I find them really helpful. So, okay. Does anyone have any other questions?
There was just a question about someone was in late about part 1. I gave a bit of a summary of that, but we do have, I know you have the slides available. There's a question about use of an oscilloscope. Do you use that or have use for it?
I haven't used one. Yeah, like I said, the materials that I bought were the only ones that I could afford at the time, honestly. But I mean, I know there's definitely a lot of really good use that you can get out of an oscilloscope. I haven't used one personally. So.
Okay. That's all I see at the moment.
Great. Well, all right, so part 3. All right. So for part 3, I'm just going to be covering a few of the. I'm going to be talking through some of the steps that I take when I'm modifying firmware and when I'm working with chips on a board. My demo's not working today, unfortunately, so I'm just going to be talking through some of this, and then if there's questions about it at the end, I can answer those. So hopefully that's okay with everyone. So just the first thing, as I kind of briefly went through it before, this is sort of at the stage where I'm going to flip back to our. Sorry, I'm going so fast through this, everyone. There we go. Okay. So when we're going through our reverse engineering methodology and we're getting into steps, 4, 5, 6, 7, or even 3, when we're setting up a serial console, these are some of the points that sorry, let me start over on that. We're essentially at part 3, where we're setting up our serial console and doing analysis. We've looked at a firmware image, but it's not the complete firmware image. So where do we go from there? We want to set up a serial console to do further analysis. Okay, cool. And we just speed through this again. There we go. Okay. So when you're setting up a serial console, the first thing that you want to do, as I mentioned before, you want to confirm the pins on the board to make sure that you have the right pins to connect to the right pins on your adapter. So the first thing is usually the easiest, which is verifying which one's ground, and you can verify that by essentially doing a continuity test to attach each of the pins or each of the candidate pins or each of the candidate headers to a ground point on the board. And then a ground point could be anything like any of the other test pads that are flat. Usually pretty easy to find another ground point on the board. And then when it beeps, that tells you that there's little to no resistance, so it's connected to that point. I know that in some of the other research I've done, people encourage you not to use a continuity test because it does introduce a little bit of voltage into the board, which can be a bit, it can sometimes damage really, really sensitive components or sensitive ICs. I've had pretty good use with just using the continuity setting, but there's also the potential to use just direct volts or other methods with a multimeter. But essentially what you want to do is you want to be going through and confirming that each of the pins is the pin that you think it is. And some of this is just trial and error to confirm which is the TX and the RX pin. That can be a little harder to determine without turning the board on. But essentially the ones that you want to make sure that you know are the ground and the VCC, so you can connect the ground to the adapter and then avoid plugging into the VCC. And then the next thing is once you've confirmed your UART headers and you've connected to the pins on the board with your adapter, you go through the process of setting up the serial console. When you have a serial console set up, the output is going to depend on the device itself. Some devices will boot right into a root shell on serial console. Sometimes they'll have a diagnostic menu just to run diagnostic commands, which will be sort of a minified version of either the OS or just running a terminal emulator on the machine. So it can really depend, but getting that serial console set up will at least give you an initial understanding of what the ways are to interact with the device through this port, which is the serial port. And then based on that analysis, using the serial port output, sometimes you can dump a firmware image or dump different parts of memory directly through the serial console. Sometimes you can't, and then you have to go through other routes to find ways to connect and get your complete firmware image. So like I said at the beginning, there's our firmware image that we got from our vendor. It wasn't, or most likely not, the complete firmware image because there were parts that were on there that weren't included in the decrypted and decompressed firmware binary. So if you want to get that full firmware image, or you want to even just get maybe a different version than the one you downloaded, the next thing to do is usually just interfacing with your identified flash chip. So if you refer back to your data sheet or your data sheets that you found during your research, you can confirm what the protocols that are used by the chips are. So the one that I found uses SPI, and it has helpful diagrams to tell you which pins are which parts, or which pins are connected to which part of the SPI protocol. So which pin is the clock, which one's the chip select, etc. And then using that information, you can hook it up to something like a bus pirate directly. So have something where it's essentially clipped right onto a chip. And then you can run something like flash ROM and dump a firmware image directly from there. Sorry, like I said, my demo kind of broke before. So this is just me talking through some of the steps, but if anyone has any questions on any of that, let me know, or if anyone has questions on anything else. That about wraps it up. Oh, actually, sorry. Just, I guess the last point that I wanted to mention, one thing that I do that I find really helpful that anyone else might find helpful in their hardware hacking experience is to actually draw out some of the board. Now this can be like a gargantuan effort if your board is very complex, especially like the one that I'm working with. And there's a ton of traces and a ton of different chips. But on simpler boards, or even just on isolated areas of a board that you're interested in, I find this to be really, really helpful. One thing that you might want to do if you're trying to interface directly with a chip, like say in this case, this example one is a serial flash chip and it uses SPI. You have your 8 pins, but your 8 pins are also connected to test points on the board to verify some of these test points. One thing that's really helpful, or that I find very helpful, is to make a drawing of it so that rather than physically tracing on the board with your hands and getting dirt on the board or something, you can just follow it by drawing it. Not everyone likes drawing, and it's not helpful for everyone, but I think it's really, really helpful to both have a diagram of it to refer to later, and also to use in identifying different components and different traces. So anyway, that's just an idea for anyone who's working on hardware hacking and is overwhelmed with all of the traces and all the components on the board. Sometimes drawing it out makes it a little simpler and a little more digestible and manageable. Again, this is just another example of doing that. So this is the same chip actually, but it's just a more detailed laid out version. And I just sat and drew it and found the test points and found which ones connected to which parts of the flash chip, and was able to solder pins to those test points directly. So that's another tip. Okay. So that about wraps it up. Does anyone have any questions?
Yeah, there was a question earlier about where you picked up the bus pirate. It was mentioned maybe on eBay, but are there other maybe other sources, good sources you find various equipment? I mean, I don't know if Amazon or any other kind of sources like that you found.
For getting a bus pirate?
Or just in general, some of the.
Yeah, I think in my work, I've mostly used Amazon for smaller parts like the header pins and the jumper wires. And then for the bus pirate specifically, I used Adafruit. And I also got my Raspberry Pi through Adafruit. Yeah, that's the one that I used. I've also I've used SparkFun pretty extensively, both for their tutorials to learn some of these things and to just have different walkthroughs. And they also have a pretty good store. So yeah, Adafruit and SparkFun and Amazon. Those are the main ones.
Cool. Yeah. All right. Any other questions? All right. I'm going to stop recording.